Hi, everyone. Today we are going to be diving into the wide world of Bayesian parameter estimation. And as a preface, I just want to say that we'll be doing some problems that we have seen before and getting the same results as we have seen before. But our goal here is to just sort of think about them from a different perspective and sort of talk about how the language that we use and the thinking that we build up to do things from a Bayesian framework. And the first thing we're going to do is we're going to measure the mean of a set of data that are drawn from a Gaussian distribution. And we know how to do this. We take the mean of the data. But we're going to reason why that's true from a Bayesian perspective. So let's assume we have a set of data that's drawn from this Gaussian, where the probability of observing a deviate xi given some mu and sigma follows the regular Gaussian function here. We'll sometimes write this as this data set big X is distributed as, that's what this little tilde symbol is. So it's distributed as a normal with mean, mu, and variance sigma squared. So we'll often say, okay, X is distributed like a normal with mu sigma squared. So if we have n samples that are observed from a distribution with a known sigma, what is the estimate of the value of mu? Again, we know how to do this. We take the mean of the data, and that gives us our result. But do we really believe that? Well, from a Bayesian perspective, what we would say is we want to figure out what is the posterior distribution of mu given the set of data x, an assumed value of sigma, and any background information in the problem. And so that's proportional to the probability of observing the data set X from a Gaussian with a mean mu and sigma, and given the background information, times the prior distribution of mu. The likelihood, we know what it is. It is the product of all of these Gaussian probabilities, and we just evaluate for a given mu and sigma, we just figure out what the probability is. So xi is plugged in, we multiply it over the n possible data sets, and that gives us our likelihood function. And again, we can assume an ignorant prior here. So a reasonable thing to do would be to say it is a flat distribution. The mean can be anywhere from mu sub min to mu max, somewhere in between. And to normalize that, we just say it's 1 over mu max minus mu min, and it's in this range, and it's 0 outside of that. And how do we pick our minimum and maximum mean? Well, the easiest thing to do would just be to take the minimum and maximum of the data and just adds a constant onto all of our probabilities. And the mean is unlikely to be outside of the range of the observed data set. You can make it even bigger if you want. For our purposes, it doesn't matter. But if we're approaching this from a Gaussian perspective, we do need to lay down a prior. So let's take a look at this. Well, here's 20 data that are drawn from a normal distribution with sigma equal 1. And you can look at this and you can see that they're all distributed around 3 to 5-ish. And here I've chosen that the true mean is actually pi. So yeah, that kind of makes sense with the data set here. So if we go ahead and we use this probability model and calculate the posterior for mu, we get a nice function here. And it looks quite reasonable. I told you that mu true was about pi, so somewhere around here, and we get a nice Gaussian function here, and it has a peak here. That is the maximum likelihood, the maximum posterior probability is estimated, and here at about 3.8. So how do we characterize this function? Well, we use the same framework that we do before. We take this is the actual result, is the posterior probability, but we often want to reduce this to simpler representations. So we write down a few quantities. So the red line indicates the true value of mu that we use to generate the data. And then the curve here has a mode at the top. That's the maximum likelihood there. And then the blue region here corresponds to the range over which that's basically the 1 sigma range for our estimate. And that is the range where the log posterior probability drops by a factor, or drops by 0.5. So an e to the minus 0.5 folding down. And that blue region there indicates the credible range where we believe the mean would be. So we're a little far off of that, but that's our value here. We can actually calculate these for this particular problem. So taking our posterior probability, we have our prior in this term, and then the product of all those Gaussian functions for each of the data. And the mode, the maximum likelihood, occurs when this is the derivative of our probability is 0. So we can calculate that, or what we normally do is we calculate the derivative of the log, because it's a monotonic function, and therefore when the log is maximized, the original function is maximized. So that gives us natural log of p. Will often give this the log likelihood variable, big L. That's some constant here, which is the sum of xi minus mu. And so if we want to figure out where that's maximized for a value of mu, we take the derivative, and our estimator here goes through, and we get a mu hat estimator, which is the mean of the data. Not terribly surprising, but I just want to flash back to what we did here, which was we used our full probability model, and because it was computationally tractable, we could just take the derivative. Out would come the max of the log likelihood function. It's well described by a Gaussian, and that gives us our estimator here that is just the mean of the data. So that's exactly what we would expect given our previous studies in physics, but we just have a different framework for talking about it. Now, for Gaussians and those posteriors that can be well approximated as such, we use this uncertainty framework, which is where delta L is 0.5, to determine the estimate, or the error in our estimate for the function. And so in that case, we can actually determine that from this Gaussian-like function, where the log likelihood is like an inverted parabola. And so as long as the higher order terms of the Taylor expansion are small, we can calculate the space over which it takes for the parabola in log likelihood space to drop by 0.5, and use that to assess what our sigma is. So we calculate the second derivative, or the curvature of that log likelihood function. We evaluate it at the mean, and given the Taylor expansion, we just solve and call that equal to the uncertainty in our mean measurement. And if we calculate that, going back to our log likelihood function here, and we calculate the second derivative, we evaluate it at the estimated value of the mean, we determine that the derivative is minus n over sigma squared, and therefore if we take the inverse negative square root of that, we get the error in the mean, which is, not surprisingly, sigma over the square root of n, because of the derivative there. So we just get all of these standard results out of the Gaussian analysis of the data in this context. So not intended to be shocking, but just intended to illustrate a previous path. So that does really well in the case where our posterior probability distribution functions look a lot like Gaussians. We can really just rely on these previous results. But what happens when we start to get things where our posterior distribution is asymmetric? And this raises the questions of the ideas of confidence intervals, though in Bayesian analysis, we like to call these the credible ranges for a property. So slightly different language. So let's consider this posterior distribution. You can see it's got a little bit of a tail over there. In that case, the mode of the distribution isn't sitting at the middle of the distribution. It's slightly off to one side. So we'll often think about what happens for the mode as the peak of the distribution. We'll also sometimes discuss the expectation value for a parameter. So if this parameter is theta, then the expectation value of theta is just the mean, the integrated mean of theta over the probability. So it's basically the center of probability mass. We also have that blue range there. That credible range is the 95% confidence interval. And we just choose our theta 1 and our theta 2 such that the integral of theta 1 over theta 2 over the center of the distribution gives us 95% of the probability. So that gives us this range here and allows us to have asymmetric uncertainties using this kind of direct integration. So just like we did in terms of parameter estimation earlier, we would essentially find out the posterior probability and then estimate what its the ranges of theta 1 and theta 2 were in order to give 95% of the probability mass inside that range. So you have to be fairly careful to make sure that your data model agrees with your results. So an example of that is what happens if you have you perform this analysis, say using the Gaussian data analysis, on data that are not actually drawn from a single Gaussian with known standard deviation. Well, in that case, your probability does not reflect the underlying true properties, the true means of a distribution. So in this example here, we have some parameter mu for the distribution, and it's drawn from a blend of two Gaussian distributions. So that's shown here. And we have this distribution of data that's drawn from that. They're slightly imbalanced here. And if we assume that that data model is all from a single Gaussian, we will come up with a very good estimate of what the mean of that Gaussian is. That's shown here in this sort of central line. So that will give us a mean value, but it doesn't actually correspond to the underlying data and the underlying distribution. You may not care. You may only be concerned that, okay, the mean of this result is the mean of the data, and that works really well, but you aren't actually characterizing the underlying data model very effectively, and you'll end up with a very low probability that a single Gaussian is a good representation of these results. So what happens if you end up with a multimodal posterior distribution? This happens quite a bit as we get further into science here. And so in this case, here's a nice multimodal estimate of some parameter. We don't know exactly what it is, but it shows that it has three distinct peaks. None of them are dramatically larger than the other. So how do we actually describe these results with some concise summary statistics? Well, there's a bunch of different strategies, and it depends on the problem and what you're trying to accomplish. You can go through and look at your posterior and pick out the modes of it. You could say that there are three distinct peaks here, and you could write down the widths and the locations of each of those peaks and describe that as a representation of the posterior. You could just calculate the expectation value of this whole distribution, finding it's actually not very likely, but it, somewhere around 4, but it may actually represent the, center of the distribution well, and that may be what's suitable for your results. You can also draw a threshold and identify the region above that probability threshold and then describe its associated width. But generally, your best bet is to just show the posteriors. They may not be perfectly tabulated or a nice compact functional form, but you can just illustrate what's happening in the data and say, this is our posterior distribution before you quote any summary statistics of it. And that's probably the best result because remember, your posterior is your core result from a Bayesian analysis. And then all of these summaries on it are just kind of flattening it down into concise single numbers. The next thing I want to talk about is a brief sidebar and remind you about the transformations of random variables. We mentioned this a little earlier, but this comes up and is very useful for doing a lot of the science that we are studying. So just recall that if you have a random variable, x, and some variable y that's a function of it, we can figure out the probability distribution functions for y if we know the probability distributions for x. So in this case, we can say, well, consider what happens if we have some p of x and p of y, and we want the probability that x is in some range delta x around x naught, and probability of y is in some range around y naught, delta y around y naught, and we want this statement to be true that the probabilities that if x naught and y naught correspond to each other, then those probabilities should correspond to each other. And so if we equate those two and do the standard abuse of differential forms that physicists like to do, divide through by the delta x and pass into the infinitesimal limit, we get this nice transformation, which basically says the probability of x is equal to the probability of y times dy by dx. Or you can have in higher dimensions where x maps to y for n total quantities, you get the probability of x, a set of x, like a vector of x's, is equal to the probability of a vector of y's times the Jacobian of the function between the two variables. So that gives us this nice transformation result that allows us to map from one variable set to another. And so we'll use that momentarily. We want to use our toolkit here to take a look at a cautionary example and illustrate the benefits of knowing the full posterior distribution of a set of data rather than trying to calculate summary statistics for it. And so this is a classic, it's called the lighthouse example. The lighthouse, we consider a lighthouse over here. We're going to assume that it is out on the water above a shore, and it is located at a position x naught and y naught, down the shore from the origin and then out to sea some distance y naught. Just to make the math a little easier, we'll assume that y naught is known, and we're trying to figure out where the lighthouse is located off the shore. And we're going to do it in the most arcane way possible, where this lighthouse is going to be spinning around, and whenever it's going to be emitting a light beam periodically. It's a highly collimated beam, and it's going to fly out, and it's going to hit the shore at some position xi, and we're going to measure that position along here because we've set up a giant array of photodetectors or something like that. So we're going to assume that the lighthouse is turning uniformly, and basically as long as it's between angle here theta I, between minus pi and pi, a light beam will hit the shore somewhere, and we'll record that position here. So this is the model for what's happening, and we can just do some geometry to figure out how this works. So using the powers of trigonometry, we get that the tangent of this angle is going to be xi minus x naught divided by y naught. So I can put that up here and say y naught tan theta is equal to xi minus x naught. And then the probability of an angle theta, sending a pulse that hits the ground on the shore, given x naught, y naught, is just going to be 1 over pi, and it's going to run between minus pi over 2 and pi over 2. If it's outside of that range, the beam never hits our infinitely long shore. Now we need to use that transform probability. So what we'll do is we'll take the derivative of this expression with respect to x. And so you get y naught secant squared, which is 1 over cos squared, d theta by dx is equal to 1. And then we say the probability of xi given a theta and y naught and an I is the probability of that theta, which will just be this uniform value, times that derivative. And so if I solve this for d theta by dx and put it in absolute values, we get that this probability of xi given theta, y, and I is cos squared theta I over pi times y naught. So that's just solving this expression. And then I can use the variables in the expression to, or in the geometry, to replace this cos theta with the lengths that are known. So cosine is the adjacent over the hypotenuse, and so that gives us this term here, cancel out a y, and we get this kind of distribution of xi given how theta I is turning. And this raises alarm bells because our probability of xi is this Lorentzian or Cauchy distribution here. And the thing we remember about the Cauchy distribution is that it has infinite variance, and that's a problem, and it's going to be the heart of why this is an interesting example, cautionary example. So let's assume we measure pulses in a sample up to about 1,000 different locations along the shore. We want to figure out where xi is. And I generated 10 random positions, and here they all are. And one of these numbers is very much not like the other. So minus 130, and all the rest of these are closer to 0. And that's the probability of these strongly tailed distributions. You occasionally get fluctuations that are very far from the middle. So with that in mind, let's think about how to estimate x naught in this Bayesian framework given everything that we know. So this, in Bayes' theorem, should be proportional to, but will, forgive me switching into equal signs. So the probability of x naught given the data set, a known value of y naught, and the background information is the probability of generating the data given x, y, and then the probability of x given y and I. So for a single datum, we use the Lorentzian distribution, and then we will assume a prior on x naught from the minimum to the maximum of the data, which when we take the logarithm of the probability, or we end up with a constant here, plus the sum of the natural log of this function. So that gives us our value. And what's neat about this is that we can immediately start inferring where that lighthouse is from our first datum. So much like we did with the coin toss in the last video, here is the posterior distribution of where that lighthouse is located here. And I'm going straight into plotting things on a logarithmic axis here. So this is the log posterior probability plus a constant. And then this is the location of the lighthouse. And the true value here is shown is this green line. And the mean of the data, one of them, shows up here in the red line. And we get this nice distribution here, and that would allow us to figure out what the location of the lighthouse is. So let's add a datum to it. This is looking good. We are the posterior is right here. The mean of the data are right at the peak of the posterior distribution, and the true data is right here. So things are looking good. But eventually, we get that weird random negative deviate at minus 132 at 0.5. And so in that case, suddenly things get a little wacky. So here's our log probability. Our mean of our data is down here at minus 25, but our posterior distribution is still peaking close to the true value of where the lighthouse is located. You can see there's a little asymmetry. There's a little shoulder here on the side of this distribution. So that's just building up our posterior. And what's important about this data is that it doesn't have a nice closed form solution for what the maximum of the posterior is. We end up calculating this numerically. And sort of see how this proceeds. So I can add progressively more data. So there's 5 points. There's 50 where our posterior is shaping up there, and where our mean is coming back to the center. 100 data, 1,000 data, it builds up there, and then yeah, that's how many data sets we have. So I'm going to actually flip back through these pretty quickly. And you'll notice that in log space, they kind of always have the same shape. They're not, you don't see the tails thinning in much the way you did with, say, the coin problem previously. And the reason that is, or we shouldn't panic too much, is remember that we are in a logarithmic space, and the vertical, like these graphs are auto-scaled here. And if we go to a linear probability, things look a little bit better. So this is a linear probability for a single datum. Here it is after 50, and we are seeing a little bit of a sharper spike, though recall that the mean of the data is still very far excluded from here, whereas the relative probability of the posterior does include the mean of the data set. So the nice thing about this is that this probabilistic posterior probability framework allows us to treat data sets that are otherwise poorly behaved and have the infinite tails and other things that will confound our statistical analysis. The posterior will still give us the information that we need. The next thing that we should talk about is the idea of multidimensional parameter estimation. So let's return to our estimates of a Gaussian data set. But let's assume that we have a data set where we don't know either the mean or the sigma parameter for the Gaussian. And we give you 20 data that are shown here and are trying to come up with the best estimate of what mu and sigma are. Well, in the Bayesian framework, we go to writing down everything we know about the model. We assume it's a Gaussian, and we will assume that we have a prior distribution. So looking at the data set that we have, it kind of looks like the mean should be somewhere between 0 and 5. And then we're going to assume that the standard deviation parameter sigma is going to be larger than 0 based on what we see. And so we'll set that up as our prior there. I put a large cutoff on it, though you can have improper priors where you simply say it's larger than 0 and are tabulating it on a domain. In that case, the log posterior data distribution has the form where you have the chi-squared like term, x minus mu quantity squared over 2 sigma squared here, and then it picks up this extra term which is related to the width of the Gaussian, and so it basically pulls down the distributions when the Gaussian width is a little larger. So given this density distribution, I can, instead of tabulating my posterior as a one-dimensional value, I brute force tabulate my posterior at every value of mu and sigma in a parameter space, and I make a plot of that, and that's shown here. So the color scale and the contours illustrate the same thing, showing different values of mu and different values of sigma. And we get this nice two-dimensional parameter space representation where we can see there's a concentration of probability here, and we have a specific point that is the maximum posterior probability of this function. When we have a two-dimensional data set, we can then explore what the probability distributions of the parameters are individually through this process of marginalization that we mentioned in the last video. Now, what marginalization does is it integrates or flattens this PDF by integrating over the parameter that you don't care about. So in this case here, this marginal plot here is supposed to show the posterior distribution of mu, and all I do is I integrate it over the x direction. In that case, that's the sigma parameter. I integrate it over that, and I get this nice distribution here. And so that is the analysis that we would carry out if we cared about what the value of mu was independent of sigma. We can also integrate this in the vertical direction and marginalize over all values of mu, and that'll give me a distribution of sigma. You notice this one's a little tailed here, so it has this asymmetric tail. And this kind of analysis is particularly important if we don't care. So let us go ahead and say, in this case, we don't actually care about what sigma is. We still just want to find the mean of the data, but we don't know we don't know what sigma is. We integrate over that. And if you go back to your log likelihood function and you integrate over the sigma parameter and then maximize that value, you once again find that the mean is the appropriate estimator for the central value of the Gaussian distribution, mu, and then you can calculate this curvature term, the second derivative of the log likelihood with respect to mu, and there you end up finding out that the uncertainty in the mean is just this value here, and you can take a look and sort of squint and see a thing that you know. So this is the square root of n. So it would normally be sigma over the square root of n, and then this is 1 over n minus 1 times the standard deviation parameter, so x minus the mu estimator squared, added up over all the data, which is exactly what we derived before, but this time we have this full framework for it. And so what this says is if I don't know my sigma, I get a pretty good estimate of what the error in the mean is using the empirically determined value of the standard deviation divided by the square root of n. So that gives us this nice framework. Marginalization allows us to treat both of these functions. I could actually say, I don't care what the mu parameter is, and I would use this posterior distribution and characterize it to figure out what the values of sigma were. So we have this great framework for kind of discussing these two parameters independently. So these two-dimensional problems work well. This is a nice problem because you can see that this sort of contours here are nice and oriented with respect to the x and y axes of the plot, which indicates there's no covariance between these parameters, and we can interpret the sigma and the mu parameters separately. But what happens if we have a covariant problem? And so I want to kind of discuss this with another example here, which thinks about the idea of looking at starlight through an optical spectrometer onto a CCD camera chip. And so the spectra will disperse onto, the light will come through the spectrometer, it will disperse, and it will hit the individual pixels of a CCD. And we want to estimate whether there is a spectral emission line at a known wavelength on top of a star's background continuum. So we will assume that the line is in emission, and we will assume it's sitting on top of a stellar continuum. And that means that we can write down a data model for how many photons are coming in as a function of wavelength. So I'll write this as R, and that's just a Gaussian function with wavelength and width. And then there's this extra background term, which is associated with the stellar continuum. Sigma is usually fixed by an instrument, so we can treat that as a fixed parameter here. And then the spectral range is discretized into pixels, which are measuring individual photons. Stars are faint, or the interesting stars are faint, so we only have a few photons. And so if we collect a data set here, we get a result that looks a little something like this, where I plotted on the x-axis, that's the separation of the line wavelength from the known wavelength. And then this is the number of photons that are detected. And then maybe there's a spectral line here, maybe not. So we would like to figure that out. We're going to assume a data model where those photon counts are set by Poisson statistics, and those Poisson statistics come from a rate equation that is just given by this Gaussian data model that we had before. And then the counts in each bin have the functional form that the probability is just given by this Poisson distribution. So the probability of finding n counts in there are set by the Poisson distribution. And then we need to lay down priors. So we are going to assume a fairly simple prior distribution right now. So the probability of A and B, given the information, is just going to assume that it's within a box of A max by B max in this two-dimensional space, and it's going to be uniform within there, zero otherwise. So we're going to assume that the background is positive or non-negative, and that the amplitude of the line is non-negative. And we want to assess the probability that we think that that line is there. So we have then a posterior probability distribution from Bayes' theorem. And then we just have that that's 1 over the prior times the probability of the observed data set given our rate model. And then this is treated as a function of the amplitude of the spectral line and the background signal. And so that's just the standard data model. And if we take the spectral line profile that we were looking at, so this, and we calculate it across all of the channels that we see here, we get a probability density function for the posterior that looks like this. So there's an A parameter and a B parameter. And what's kind of cool about this is you can see pretty clearly that despite this looking like the least inspiring astronomical data of all time, if we have a good data model, we can actually get reasonably good constraints on the background and then the amplitude. So, and that's pretty good given that we ended up with our actual data used to generate it was about here. So well within our credible range of parameters. So you can also notice that the width of the distribution for A and the width of distribution for B are very different from each other. The A distribution is, it goes down, and there's significant probability at 0. And even up here. So there's a very wide spread in the amplitude of the spectral line, possibly including 0. And then the second line, the background here, actually is fairly well constrained. And that makes sense because there's lots and lots and lots and lots of data here that have background signal, and there's only a fairly narrow range where there's contributions to lines. So we end up with a very good estimate of the background in this information, whereas the amplitude is a little more poorly constrained. So that gives us these nice framework for approaching all of these problems in terms of parameter estimation from this Bayesian framework. So we get overall similar stuff to the frequentist view, but on average, we've been assuming very non-informative priors, even though the framework is a lot more general. So now we'll sort of move on into the idea of what are better priors to assume in more sort of challenging frameworks.